Hello and welcome to day 3 of Unit 5. Let's get started because today's a big day. We're going to start talking today about the area problem or the area model and looking at area under a curve. Excuse me, I'm just cleaning my whiteboard here. We're going to be doing a lot of writing today. So the first thing we need to talk about is sigma notation. Sigma notation is going to be used a lot throughout this unit. And just for your own penmanship purposes, the best way to write a sigma is a big equal sign with a greater than symbol in the middle. Otherwise, you end up with something like that, and then it becomes hard to write on top of. So don't do this, do that. Okay. Now, there are a lot of properties of summations. You can scale them, you can add them, you can subtract them. Okay, those are the basics. But there are also a few others that you need to know. Okay, so let's see. The sum as k goes from 1 to n of 1 is just 1 plus 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 1 n times. So it's n times 1 or n. Okay? Now the next one actually has a story that goes along with it. It's k equals 1 and goes to n of n. Oh, excuse me, k. Okay. That's the sum of n consecutive integers. N consecutive whole numbers, actually. Natural numbers. And the story goes that the young mathematician Gauss was in his math class, and a teacher asked the class at the beginning of class as a warm-up, I want you to add up all the numbers from 1 to 1,000. And boom, Gauss had the answer. Now, how did he do it so fast? Well, he was smarter than the numbers. He said instead of adding up 1 plus 2 plus 3 plus 4 plus 999 plus 1,000, instead, I'll just add 1 to 1,000 and 2 to 999 and 3 to 998 and so on. He'll add 2 to 999 and 1 to 1,001, and in each case here I get 1,001 and I get 1,001 here, and I get 1,001 here, and so on and so forth. I get 1,001 for every one of those pairs of sums. And how many pairs of sums do I have? 1, 2, 3, 4, ... 1,000. I have 1,000 1,001s. So I have 1,000 1,001s. However, notice that I've added 1 to 1,000 and 1,000 to 1, so my sum is twice as large as I would want it to be. So I'll divide it by 2. So the answer to this problem here is 500. Let's see. Half of 1,000 is 500, and half of A million is 500. Oof, math. So, how does that play into this? Well, that problem is this problem in general. It's 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8, all the way up to n, the number n, which could be whatever number you want it to be. I could put 1,000 there. I could put 10,000 there. But all this is going to be equal to is n times n plus 1 divided by 2. And that you need to know. As do you need to know k squared. So that's the sum of consecutive squares. That's 1 plus 2 plus 4 plus 9 plus 16 plus 25 plus 36, all the way up to some number n squared. Okay? And that's going to be n times n plus 1 times n plus 3. Oh, excuse me, 2n plus 1. All divided by 6. Okay. Again, something that you just need to know. Okay. And the last one that doesn't come up as much, but could possibly come up, is the sum of consecutive cubes. And the sum of consecutive cubes comes out to actually be n times n plus 1 divided by 2 squared, which is really interesting, right? Because basically what that's saying is the sum of consecutive cubes is equal to the square of consecutive integers. Now, but we're not going to concern ourselves with that because it's not the question at hand today. The question at hand today is length times width, area. But we're going to be taking lots of areas, and we're using sigma notation to add those areas up. So we did need to have a little bit of background knowledge. Okay. So this is need to know material. Okay, before we can get started. Okay, so here's our first real conundrum in calculus. And that is, I want to know what the area underneath this curve is. Well, it doesn't have straight defined edges. They're kind of curvy. So I can't use any formula that I know from geometry to get the exact area, but what I can do is estimate it. So let's start by estimating it this way. What if I drew sort of a rectangle like this? Now, there's a lot of error here. For instance, here, there's a little tiny piece of area that I'm going to calculate that's outside of the graph. It's not underneath the graph. It's not exactly where I wanted it, but maybe it gets taken up into account where all the other error happens. Now, how can I make this estimation better? First of all, I want us to note that these rectangles are equally width apart. Okay? Equally width apart. Okay? And that width is going to be called delta x. It's just the change in x from some given x sub k value. The next one is x sub k plus delta x. Okay. Well, let's try a different estimation, and let's do twice as many boxes. Okay. So now we got this. All right. So now I sort of got this going on. And this is starting to look a lot better. Oh, I think we can do better. Let's divide these yet again in half. Oh, that seems to be a lot better. Let's remind you where my graph was here. Okay, well, that green area seems to be even a better estimate of the area underneath the curve. And all I've done there is make the width of each of these rectangles smaller and smaller and smaller and smaller. So, what am I doing? I want to add these rectangles up. So we have to find out the area of one of these rectangles. Well, like I said, the width of these rectangles is delta x. Okay. The height of these rectangles is the value of the function. It's whatever f of x is at some given x sub k value. Okay. So that is the area of one rectangle. But I want to add up a bunch of rectangles. And I want to add a bunch of rectangles up from some point to another. Okay. Now, what I want to do is I want the number of rectangles, which is what this n is, to approach a very large number. And what does that imply? Well, let's take the limit as n goes to infinity. And the limit as n goes to infinity of the sum as k goes from 1 to n of f of x sub k delta x is the definition of area under the curve, which for our purposes in this course is going to be considered the definition of integral. And we're going to be using this in the next few examples to determine the area under some given curves. Okay. Now, a few things that we need to clear up. How do I find delta x, that change in x? Well, if I know the number of subintervals that I want, and I know where I'm starting and where I'm ending, then delta x is just your end minus your start, or your distance, divided by the number of subintervals that you want. Okay. Okay. Okay, so before we actually start using the definition of area under a curve, let's take a geometric look, or a geometric approach to finding or estimating the area underneath of a curve. And that estimation, or that process that I was using before of subdividing the area under the region under a curve into rectangles, is called a Riemann sum. Okay, so we want to evaluate the Riemann sum for the graph 5 minus x squared, which looks something like this, for x is between 0 and 2. Okay, so let's see, 2 is I think like here-ish, and we want 4 subintervals. So that's 1, and that's 0.5, that's 1.5. There's my 4 subintervals. And here's my 4 rectangles. And now it's pretty clear what the areas of these guys all are. Well, the width of each of these is 0.5. Well, we could find that using the formula for delta x, right? Delta x is the end minus the start divided by the number of subintervals, which is 1/2. Okay? And the various values of k are found by starting at 0 and adding delta x. So x sub 1 is going to be zero plus 0.5, which is 0.5. X sub 2 is going to be 0 plus 2 times 1/2, which is 1. X sub 3 is going to be 0 plus 3 times 1/2, which is 3/2, and so on and so forth. So to add up all my areas, right? It's just the sum as k goes from 1 to 4 of f of x sub k times delta x, which is just f of 0.5 times 0.5 plus f of 1 times 0.5, f of 1.5 times 0.5 plus f of 2 times 0.5. Okay. And this sum comes out to something like 25 over 4. Very nice. Now all I've done is take these rectangles and use the analytical geometry to add the areas. And that's called, that's called a Riemann sum. Okay, so before we move into using the definition of area under a curve in a real application, given a function, find the area under the curve using the definition, I want us to first practice some of the computation involved, and therefore we're going to look at finding the value of this limit. Okay. So the first thing I'm going to do is try to simplify things, not forgetting to write my limit every single step of the way. Okay, I'm going to square k over n, and I'm also going to distribute in the 1 over n. Okay, so we get a k squared over n cubed plus 1 over n. Okay. Now, with summations, we can, remember we said we could add summations, we can scale summations. The thing that we have to keep in mind is what here is a constant and what here is changing. What is the same in every single term, and what is different in each term of the sequence. Okay? And in this case, k is the thing that's being incremented. k starts as 1, and then it's 2, and then it's 3, and then it's 4. It goes up to n. N is the constant. Okay? Now, yes, we are taking n to go to infinity, but for the purposes of the summation, n is constant. It's not changing. It's not being incremented. So anything with n in it can be pulled out of the summation. You can also break this summation up into the sum of sums, if you will. So that's what we're going to do. We'll have the limit as n goes to infinity of 1 over n cubed times the sum as k equals 1 to n of k squared plus 1 over n. So the summation as k equals 1 to n of 1, right? Well, we talked about these things. We talked about those things earlier, right? They have definite values. And this was something like n times n plus 1 times 2n plus 1 over 6, right? And this was just n. So, what does this limit come out to be? Well, that's just 1. And this is going to be an n squared, and then eventually times another n is going to give me an n cubed. And it's going to have a 2 in the numerator and a 6 in the denominator. So I'm going to get something like 2n cubed plus some stuff all over 6n cubed plus some stuff. And what's the limit of this as n goes to infinity? Well, it's just the n behavior of that rational function, which when the exponents are the same, is the ratio of the leading coefficients. And in this case, that's a third. Okay, so this is just a third, and my limit comes out to be 1/3 plus 1, or 4/3. So the answer to this bad boy here is 4/3. We'll write it up here too, so you can't mistake. 4/3. All right, so wrap things up. We're going to look at bringing this all together and trying our hand out at a definition of area under the curve problem. So we're going to use the definition of area to find the area under the curve 5 minus x on the interval from 0 to 4 with x star sub k as right endpoints of each subinterval. And basically what that means is that my bars that are going up are hitting the graph on their right, okay, as opposed to their left or their midpoint, which is something that we'll talk about eventually. But just keep that in mind that, you know, if I had a curve like this, the right Riemann sum is where the right corner of that bar goes up and hits the graph. So, some things we need to know. We need to know what delta x is. Delta x is the start, or excuse me, n minus the start divided by the number of subintervals. And in this case, I don't know the number of subintervals. In fact, I want the number of subintervals to eventually be infinity. So in this case, delta x is 4 over n. Okay? And in this problem, I don't know how many subintervals I want, so there's no way to find delta x. So that means that various values of x are going to go from 0, and I'm going to add delta x in increments of k. I'm starting at 0, I'm going to 4. Okay. And every x value is being incremented by delta x and k. So x star k is 4k over n. Okay. And f of x star k is 5 minus 4k over n. Okay. And f of x star k delta x is 20 over n minus 16k over n squared. Okay. Now I'm just taking this guy and sticking him in there and doing exactly what we did in that last problem. I want the limit as n goes to infinity of the sum k equals 1 to n of 20 over n minus 16 over n squared k. And just like I did before, I'm going to break this up into two summations. I'm going to pull out the things that are constant, the things that aren't being incremented, and just sum up. Let's bring this over here so I have a little bit of room to write here. And I'm just going to sum up the things that are being incremented. That's the k's. Okay. So we have 20 over n sum as k equals 1 to n of 1 minus 16 over n squared sum as k equals 1 to n of k. And we know that this is equal to n, so I get 20 over n, or just 20. And this is equal to n times n plus 1 over 2. And now the limit of this, well, that's n squared. Oops, I forgot the n squared there. That's n squared plus some junk over n squared. So it's just the ratio of my coefficients there, which is 16 over 2, which is 8. So my limit here is just 20 minus 8, which is 12. Alright, now how can I check this? Well, let's think about what this is. This is just a line, 1, 2, 3, 4, 5, starts at 5 and has a slope of negative 1. So it goes like that, and all I wanted to do was find the area from 0 to 4. Alright. I just wanted to find this area. Now, I think the easiest way to find that area is trapezoidal, right? It's 1/2 the sum of the bases, which is 1 plus 5 over times the height, which is 4. So that's 2 times 6, which is 12. Checks out. The definition of area of 5 minus x on the interval from 0 to 4 gave me 12. And when I did it geometrically, I got 12 as well. Okay. So have fun with these problems. These are fun problems. Okay.